Hi, to whom it may concern. Today we're presenting the dark side of the apple. We are the Pasquel's team, and we are Sofía Gabriela Padrón Rodríguez, our captain, Elena Saray Chávez Hernández, and Jorge Mendoza Luna. Our assessor was Martha Yolanda Sanchez Muñoz, and we come from high school number 9. Imagine slicing into a crisp, juicy apple, only to find it gradually turning brown before your eyes. This natural phenomenon, known as enzymatic browning, has puzzled scientists and apple enthusiasts alike for years. Today, we embark on a journey to uncover the mysteries behind apple browning and discover effective methods to prevent it, all while ensuring the apple remains as delicious and nutritious as ever. Enzymatic browning occurs when certain compounds in the apple, such as polyphenols, react with oxygen in the air. This reaction is catalyzed by enzymes present in the apple tissue, resulting in the formation of brown pigments. But what factors influence the rate at which this browning occurs? Through extensive experimentation, we've identified 5 key factors that play a crucial role in the browning process. Air exposure is the first one, then enzyme activity, then the pH level, the temperature, and lastly, substrate concentration. Understanding these factors allows us to formulate a hypothesis. Increased air exposure, higher enzyme activity, neutral to slightly acidic pH, higher temperatures, and elevated substrate concentrations will accelerate the browning rate. To combat browning, we've explored various chemical inhibitors that can effectively slow down the enzymatic reaction. Ascorbic acid, citric acid, and sulfites have shown promising results in inhibiting enzymatic browning by either blocking enzyme activity or scavenging oxygen to prevent oxidation. However, the challenge lies in finding an inhibitor that effectively prevents browning without compromising the taste or nutritional integrity of the apple. We seek a solution that strikes a delicate balance between preservation and sensory quality. As we continue our research, we're also investigating the correlations between browning rates and the factors we mentioned before. By understanding how these variables interact, we gain deeper insights into the mechanism underlying enzymatic browning. Our ultimate goal is to propose an anti-browning solution that maintains the freshness, flavor, and nutritional value of apples while minimizing undesirable changes in the chemical composition. We envision a future where apples remain as crisp and juicy as the day they were picked, offering consumers a delightful and wholesome snacking experience. Enzymatic browning in apples is a multifaceted process influenced by a myriad of factors. Through diligent experimentation and innovation, we strive to unravel its complexities and develop sustainable solutions that benefit consumers and apple enthusiasts worldwide.
For studying the investigation, it was important to know why the apple got brown. This question have two answers: the Maillard reaction, also known as non-enzymatic recordation, and the enzymatic browning. The first one is a chemical phenomenon in which reducing sugar react with amino groups of proteins. And the second one is when apples are colorless, they are exposed to air, and the phenolic compounds present in the fruit are oxidized by an enzyme called polyphenol oxidase. Polyphenol oxidase, or PPO, are tetamatic enzymes that contain 4 copper per molecule. It is responsible of the darkening of damaged fruits and vegetables by catalyzing two different reactions, such as the addition of monophenols to diphenols and the oxidation of diphenols to alkenols. To try to inhibit PPO activity, it's important to consider that his pH of 5 to 7 shows emission below pH of 3, because that all opportunity areas are the reducing agents that prevent enzymatic browning by reducing alkenols to unchloride or diphenols, the antioxidants that are molecules capable of preventing or delaying the process of oxidation of other molecules, and the chelating agents that are those that can form stable complex chelates, are other complex compounds that attach to a large molecule called ligand in a ring structure. After analyzing, Weiss found out that the ascorbic acid is the better option of the resolution of the problem, since several studies have proven its effectiveness inhibiting the PPO reaction. Some of them demonstrated inhibition of up to 95.65% with a concentration of 1380 ppm.
After our first experimentation process and choosing ascorbic acid as our PPO inhibitor, there are some physical factors to discuss. As various papers and studies have shown, temperature is also an important factor in the enzymatic browning, as well as the oxygen availability, as oxygen is the first factor of the oxidation process. It's found that the highest levels of PPO activations are in between 30 to 35 Celsius, and having a considerable inhibition passing 90 Celsius or lower than 10 Celsius. For our second experimentation process, we will divide our apple slices in three groups throughout three categories. Group 1, heated in boiling water before being cooled down in ice water to avoid cooking for a short period of time. Group 2, placed on the fridge at minus 10 Celsius. Group 3 were microwaved in 20-second intervals for 1 minute and cooled down quickly to avoid cooking. The first category were used as controls, as they weren't covered in anything. Second category were placed inside Tupperwares, and third category were wrapped in plastic paper. We used one from each group for one of each category, giving us 9 samples, and all 9 samples were covered in ascorbic acid. After 24 hours, the best results were the ones placed inside the toppers, continued by the control ones covered in just ascorbic acid, and the last ones were the covered in plastic wrap, as they were the worst. So, in conclusion, the best results were from the ascorbic acid as a chemical inhibitor, and as physical factors, the high and low temperature shock method, as well as preserving it in a topper-like container to preserve their original apple-like consistency.
Thank you for watching. We were the Pasquels.